Okay class, today we're going to learn about equilibrium. So what is equilibrium? Equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. In order to understand what equilibrium really means, we're going to watch this short clip called The Farmer and the Prankster. Almost all chemical reactions are reversible. In other words, both the forward and reverse reactions will occur. When the forward reaction is happening at the same rate as the reverse reaction, the reactions are in equilibrium. Imagine a prankster with a large shovel filling a well by digging a hole next to it and dumping the dirt into the well. The large shovel can move a large amount of dirt, so at first this person deepens the hole rapidly and begins to quickly fill the well. Now, the owner of the well angrily begins to use a smaller shovel to empty the new dirt out from his well back into the hole. At first, because the shovel is small and the dirt has to be moved all the way up the deep well, the well owner isn't able to match the pace of the miscreant, and the well continues to fill despite his best efforts. However, as the hole deepens, the troublemaker with the large shovel has to reach further and further down in order to dig a hole deeper, slowing his progress. In contrast, as the well is being filled, the owner with the small shovel has to move the dirt a smaller distance, so she is able to empty her well and fill the hole. Eventually, the rate at which the well is being filled is equal to the rate at which the well is emptied. Here, the depths of the well and the hole have reached equilibrium. So one thing to notice here is equilibrium is not when the amounts are equal, because we can see that there's a lot more dirt in the well than there is in the hole. And so it's the rate at which the hole is being dug is equal to the rate at which the well is being emptied. That is when we have reached equilibrium, okay? The equilibrium constant is represented by a K. Kf represents the constant for the reaction in the forward direction, and Kr represents the constant for the reaction in the reverse direction. K is represented by the equation, the multiplication, which is represented by a pi, of the products all over the pi, which is the multiplication of the reactants. The coefficients out front represent the powers that the concentration is raised to. So in this general example, we have A plus B yields D plus E. So we have the multiplication of the products, each raised to their individual powers, which are the moles, all over the multiplication of the reactants raised to their powers, which are also the moles. When Kf equals Kr, the system is said to be at equilibrium, and that is what the equilibrium constant is. The equilibrium concentration expression is when we have a reaction that contains liquids, solids, and aqueous solutions, or a mixture of them, but only the aqueous concentrations are written into the equilibrium expression. Liquids and solids are always left out. This represents Kc, or the concentration equilibrium expression. We can also have an equilibrium pressure expression. When a reaction contains liquid, solids, and gaseous compounds, only write gas pressures in the equilibrium expression. When dealing with pressures, you need to make sure that all of the gases have the same units. We've already done this, so we know that we have like atmospheres, torrs, pascals, etc. Make sure that they're all in the same unit. Once again, liquids and solids are always left out. This represents Kp, or the pressure equilibrium expression. When a reaction is not at equilibrium, we can still write an expression the same way as before, but now we use Q instead of K. Q is represented the same way. It's the multiplication of the products over the multiplication of the reactant. If K is greater than Q, the reaction shifts to the right, meaning that it's product favored, that it would rather go in that direction. If K is less than Q, it means that the reaction shifts to the left, or that it's reactant favored, and so it prefers to go in the direction to favor the reactant. When equilibrium is disturbed, we have to deal with a thing called Le Chatelier's principle. So changing concentration, pressure, or temperature affects the equilibrium expression. If a dynamic equilibrium is disturbed by changing the conditions listed above, the position of equilibrium moves to counteract the change. Catalysts speed up a reaction, but they do not affect the equilibrium expression. So anytime they ask you what happens when this catalyst is added, you say nothing. It does not do anything to the equilibrium. It just makes it reach equilibrium quicker. Another thing is adding an inert gas, which is a noble gas or a gas that does not react, means that it does not affect the equilibrium expression either, because it does not react with the things involved. The easiest way to understand the Chatelier's principle is just by having an example. So in this case, we have nitrogen plus hydrogen yields ammonia. So if we increase the N or H concentration, the amount that we have of them, because they're on the left side, if we increase them, we need to counteract it by getting rid of them, so it's going to shift to the right, making it favor the NH3. If we decrease N or H, then it's going to shift to the left, because now it needs to increase those. It has to counteract what it just did. If we increase NH3, it's going to shift to the left because it wants to get rid of the NH3 and produce more N and H. If we decrease the NH3, it will shift to the right, just like before, because it wants to produce more NH3. The next thing is with pressure, though. If you increase the pressure, that means that you reduce the volume of the container. If you reduce the volume, it's going to favor the side with less moles of gas because they react to take up less space. If you have a little space, you want the least moles of gas, or they become too crowded. So in this case, we're going to favor the side with the less moles. You can think of this like as some people. If you have single people, then they take up a lot of space, but when you have couples, then they get closer together, and so they take up less space. So if you have a small room, you want couples, because couples don't mind being close to each other, and so they take up less space. It's going to favor the side with less moles. If we decrease the pressure, which means we increase the volume, it's going to favor the side with more moles of gas, because now if you have a ton of space, those individual molecules want to be by themselves, because they'd rather be by themselves and have as much space as they can than have to react and combine with somebody and share electrons. So when you decrease the pressure and increase the volume, you're going to favor the side with more moles of gas. The last thing that can affect it is temperature. For an endothermic reaction, we've already learned that in endothermic reactions, heat is absorbed, which means it's on the left side of the equation. Once we know which side the heat is on, we treat it just like we do the concentration or the amount of the thing that we're dealing with. So if we increase the temperature of an endothermic reaction, it's going to shift to the right towards the product to get rid of the heat. If we decrease the temperature of an endothermic reaction, we're going to shift towards the reactants because we need to get more heat. It's the same way for exothermic reactions. We learned that in exothermic reaction, heat is let off. If heat is let off, then heat is on the right side of the equation, and you treat it the same way as we did the concentration. So if you increase the temperature of an exothermic reaction, it's going to shift towards the reactants. It's going to shift to the left. If we decrease the temperature, it's going to shift to the right to produce more heat. So these are the basic things that we're going to talk about with Le Chatelier's principle and with equilibrium. And so now you guys are going to have a worksheet that you guys are going to do with a bunch of examples to learn more about equilibrium and to understand the concept. And this will prepare you for the labs we're going to do during this week and next week, okay? You guys have a wonderful day, and thank you for your time.